I'm waiting for that chime to get going. There it is. All right, BC Calc students. Today, we're going to be doing the trapezoidal rule and Simpson's rule, which are two different ways of estimating areas under curves. When we use Riemann sums and the rectangular approximation method, those are largely to build the framework for doing integrals, for getting exact answers to things. And yet the trapezoidal rule and Simpson's rule are actually used by your calculator when it calculates areas. There's numerical methods to try to get the area under a curve more accurately within a finite amount of time. If you had, you could use rectangles to get areas exactly, but it would technically take an infinite amount of time. If each rectangle you spent time calculating, you'd have an infinite amount of time, which is not practical. And so engineers and mathematicians have devised ways to approximate things more accurately. And two of those ways are the trapezoidal rule and Simpson's rule. So let's just be really clear about the current knowledge we have. So Riemann sum, the first thing is we're going to use rectangles. Both these methods we've done so far use rectangles. Today's methods will be different. But a Riemann sum allows for the subintervals not to be of equal width. And that's really important. They can be if you want, and we will see problems where they are, but generally they don't have to be. And then, as you know, C, this value C is choose. You can choose any X value, C sub K, in each interval. So C sub 1 would be within the first interval, the first rectangle. You would evaluate at some value of X, the height of that rectangle, and so on. And you might be asked on the test to use a left, midpoint, or right Riemann sum on your test. And the reason for that is for consistency. Technically, you could choose to use any value you wanted within each interval. But if every kid does their own, then everyone's going to have different answers. And so they'll restrict you on the BC Calc test to left, right, or midpoint if you actually end up calculating one. The other one is the rectangular approximation method. And you can do the left, midpoint, or right with those as well. They will generally ask you, would this underestimate or overestimate the area? And they want to see a calculus reason like, well, it would underestimate because of the fact that it's an increasing function or whatever. So today we're going to look at two additional methods to estimate the area under a curve, and they're called the trapezoid rule and Simpson's rule. So basically, with the trapezoidal approximation method, you use a series of trapezoids to approximate the area. And from geometry, we know the formula of a trapezoid is the average of the bases times what I call the perpendicular height. That is the distance between the two parallel bases. And the width of each subinterval does not have to be the same for the trapezoid rule, but most textbooks will make it the same because there's a formula we use for trapezoidal rules. So you guys have to be careful with that. If you're going to memorize a formula, it will only be valid if all of those intervals are the same width. They may ask you on an AP Calc test to use the trapezoidal approximation using the data suggested in the table, in which case they won't be all over the same width. And so you'll have to be mindful of that. So suppose we decide for this particular function, we want a subinterval width of 2 units. So that would mean every single one of them is the same. To estimate the area under the curve pictured at left, draw in the 4 trapezoids. So basically, the first trapezoid goes here. This goes from 1 to 3. The next trapezoid is going to go here, here, and here. And then as I draw these in, basically you can see what's going on here. This is pretty darn close to the actual area of this thing. You can see a slight overestimate of the area there. I suppose a slightly bigger overestimate there and yet a bigger one here, like so. Okay, but this one is almost spot on. This trapezoid is going to slightly underestimate that area. Okay, under what conditions will a trapezoid underestimate an area like this one? In that case, the curve is concave down. The curve is concave down. In other words, if the second derivative is less than 0, then it will be underestimating the area of the curve. And overestimating is the exact opposite. If the curve on that interval, a single trapezoid, if the curve is concave up. So in other words, using your notation, if the second derivative is greater than 0, like this one here, you can see the fact that even though the function is decreasing here, this trapezoid is overestimating the area because the curve is concave up there. And then here, again, the curve is increasing and concave up. But the issue is the concavity matters for the trapezoid rule, okay? All righty, and then it says calculate the area of the first trapezoid. So it's hard to see it at the scale here, but we basically have base 1 is equal to 14, and base 2 is 12, and the height in between the two of them is 2 units. This is 1 and this is 3. So that height is 2, and so we just average these together. 14 plus 12 over 2. We know that that number equals 13, but notice I'm going to multiply by the height of 2, and so things are going to work out rather nicely there. The 2's are going to go out, and so I end up with basically the sum of 14 and 12, which is just 26 square units. Okay, and you don't have to put units on your paper if this is just in plain old units. There's no units on anything. So you could just say 26 and that would be acceptable. Okay, the second trapezoid, we have the first base is 12. The second base is, that says 10. And again, the height is 2. And so the same basic deal, 12 plus 10 over 2 times 2. The 2's go out and you end up with 22. Okay, all right, third trapezoid is here. Base 1 is 10, base 2 is 11, is that right? Boy, that's hard to see. And then the height is equal to 2, and so I do 10 plus 11, take the average, multiply that by the height, and I get 21. Okay, all right, I'm not getting the same thing that I got last year. Good heavens, so this is a little bit daunting here. That is a 14, that's why, that's not an 11. That is a 14, that is a 14. 24. There we are. Okay, so that's better. I'm comparing my notes against what I had last year. That's why I keep looking over here. I have it on the other screen. Okay, the fourth trapezoid is the last one. So base 1 is 14. Base 2 is 30. Height is 2. So 14 plus 30 over 2 times 2. We end up with 44. And so the total area under the curve would be the sum of all 4 of these. So 26, 22, 24, and 44 is 116 square units, like so. Okay, so this is just an application of using the trapezoidal approximation. Okay, all right. Now, one issue that can come up with the trapezoidal rule, and you don't have to really worry about it, but I want you to think about this. Sometimes what we are calling a trapezoid is not, in fact, a trapezoid. Consider the area of the integral of the following function. The area of the integral is kind of is not clear. The area under the curve, right? Under the curve of the following function on the interval from 1 to 14, and each subinterval suggested by the points on the curve. So if you see something like that, please be mindful. That is hinting to you, do not assume that each of these has the same width. So sketch in the 4 trapezoids. So notice here's my x-axis here. So this first one is a proper trapezoid, okay? It is going to look like this first trapezoid, like so, okay, like that. All right, so that very first trapezoid looks like that. This here goes from 1 to 4, so that's 3, okay? And that's indeed a trapezoid. But this second one, notice the x-axis is here. This second one technically is a triangle. Its base is also 3, but that's technically a triangle. Now the question is, would the formula still work? And the answer is, of course, it would still work, because your 2 bases are here and here, and this one would basically be 0. And so when you do the average of this one plus this one, you basically get half of this base and then times height. So 1/2 base times height. And so it really doesn't matter that that one's a triangle. Okay, this next trapezoid, we have basically the same problem. This one is below the x-axis. And so once again, I don't really get a trapezoid. As a matter of fact, I'm getting a triangle once again, okay? And then finally, the last one. Now, this one's really kind of wacky. This one's really got issues. This one is below the x-axis, and this one is above the x-axis. And so we end up with this peculiar looking thing here, which is not even a closed figure, right? That one is not even a closed figure. And so how do you handle that? Well, fortunately, if you look into it, notice that this is what, -3. That would be base 1 is -3. And then this one would have base 2 is 6. And so the issue that you get away with here is, well, what would happen? Let me see if I can focus this better. So the issue that I have here is what if I just blindly follow this formula that says the area of this thing is equal to base 1 plus base 2 over 2 times the height, right? Well, let's see what happens there. We'd end up with base 1 being a -3 plus base 2 is 6. Divide that by 2 times the height, okay? Well, gosh, what's going on there? Well, let me rewrite this a different way. What if I sort of distribute this h? I have -3 halves of the height plus 6 halves of the height, okay? Well, if you think about what that's saying there, that's essentially saying I would be doing 1/2 of the -3 times the height. And so it's saying, well, that would be what you'd get if you treated this height here and did a -3, right? You treated this height as a -3. And then if I calculated the other one, that would be plus 1/2 of 6 times the height. So that would be this triangle up here where it has a height of 6 and a base of 3, like so. Whatever this is, the h, whatever that height is. What is that? 1, 2? Yeah, that's 2, right? Like so. And so basically what it's telling you to do is basically add up the positive area of this triangle and then subtract the area of this triangle. And as it turns out, it doesn't really matter. In terms of your ultimate calculations of the area, it's not actually going to make a difference, okay? So all of this, are all of the subintervals of equal width? No. These are each 3, and this one is what, from 7 to 12? That's 5. That's subinterval is of width 5, and this is what subinterval is of width 2, okay? And which of them are actually trapezoids? Only this first one is actually a trapezoid, only the first. Okay, so we don't have to worry about things too much. Only that first one is a trapezoid. The formula will work out just fine here. It'll work out just fine here. And then this one's a little odd, but you have a positive contribution of area minus a negative contribution of area. So all works out and everything is well, and it really doesn't matter. You'll be absolutely fine using the trapezoidal rule. Okay. All righty. So number 3, I'm going to develop the formula that you often see in textbooks for the trapezoidal rule. And so here are some assumptions that we have to use. In order to develop the formula, I'm going to do it with a finite number of rectangles first, and then we can extend it to n rectangles. In this case, I'm going to start with 4 subintervals. So how wide is each one? Well, this one is at A, and this one is at x of 1, and this one's at x of 2, and this one's at x of 3, and that one's at x of 4. So the total distance is B minus A, and I'm going to divide that into 4 equal pieces, and so that I'm going to call H. That height of each trapezoid, I'll call H, okay? Write an expression for the total area under the curve using the trapezoidal rule. So the first trapezoid would be, its base would be y sub naught plus y sub 1 over 2 times the height, let's call that h, and then plus so that's this one. The second trapezoid would be y sub 1 plus y sub 2 over 2 times h. That takes care of him. The third one would be y sub 2 plus y sub 3, average that times h. And the last one would be y sub 3 plus y sub 4 over 2 times h. Okay, and you'll notice, well, what if I factor out the h over 2? Okay, so what if I take out the h over 2? Then I would have y sub 0 plus y sub 1 plus y sub 1 plus y sub 2 plus y sub 2 plus y sub 3 plus y sub 3 plus y sub 4, like so. Okay, and then you combine your like terms, you'll notice that this one's a singleton. There's a pair of those, a pair of those, and a pair of those. So I end up with h over 2 times y sub 0 plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus y sub 4, like this, okay? And so this is the general rule. This formula is valid only if every subinterval is of the same width. Okay, so you might be asked on a test to use a trapezoidal approximation of data in a table, and the subintervals may not always be of equal width. So just be mindful. So let me substitute here. So remember that h was b minus a over 4. So b minus a over 4 divided by 2. To simplify that, I'm going to, so h over 2, this piece here is equal to this, h over 2. And so let's think about that. That is equal to, what if I multiply the top and bottom of this fraction by 2? Well, I'm sorry, not 2. Let's do 4. I'm going to multiply the top by 4 and the bottom by 4, right? These 4's go out and I get b minus a over 8, okay? And let's think about that. Where did that 8 come from? It came from multiplying 2 times 4, okay? But where did the 4 come from? Well, remember that was n, okay? And so I basically have a situation where everything is based on n. And so I end up with this area of all the trapezoids is equal to h over 2 boiled down to this, b minus a over 8 times y sub naught plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus 1y sub 4. Okay, and if I want to generalize that, I could say the area is equal to b minus a over, this is twice the number of subintervals I had, so 2n, and then I'm going to start with y sub naught plus 2y sub 1 plus 2y sub 2 plus 2y sub 3 plus dot, 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 and then y sub n, like so. And so this is the type of thing that you will see in a textbook, okay? And you guys, if you memorize it, that's fine. Just be sure that you understand the assumptions that went into the development of that formula. We assumed we had n equally spaced subintervals, okay? And so be very, very careful with that formula, that if you memorize it, that you're applying it correctly. Okay, so this formula is rather interesting here. So what people have done is over the years, they've tried to develop increasingly sophisticated methods to calculate these things. They have all kinds of names. One of them is one of my favorite to pronounce. It's called the Runge Kutta. Runge Kutta, which is a fantastic rule. It uses these really higher order things to calculate areas. It's extremely accurate. It's pretty intensive, but you don't need that. The calculations get intensive, but you don't need that many of them to get a very accurate method. So one of these rules is called Simpson's rule. And so look at how this one works. As you may have noticed, the rectangular method approximates the function as a constant over each interval. And the trapezoid rule uses a linear approximation of the function over each subinterval. And so another method is to use little quadratic polynomials. And so this dude Simpson came up with this rule where he said, well, instead of using just a line to connect them or a constant, what if I actually fit a little parabola to each section as best I can? And so he did that. He did like a midpoint parabola, I think it is. And he uses a quadratic polynomial to estimate the area there. And so that's why you see this 3 down here. You guys know that we talked about this. If you have a polynomial, x squared, you know that this shaded area here will be 1/3 of the area of the rectangle, as long as one is at the vertex. And so that's exactly what Simpson's method does, is it uses a polynomial, and after you shuffle things around, you end up with this h over 3 here. And so in any case, it's generally more accurate than either the rectangular or the trapezoidal rule. And to use it properly, you have to be choosy about things. You have to have an equal number of equal width subdivisions, okay? And so you have to have an even number. N has to be even, and they all have to be the same width. And in that case, you would have this very complicated expression, much more complicated than what I have here. But when you boil things down, you end up strangely with 4 of y sub 1 and only 2 of y sub 2 and 4 of y sub 3 and 2 of y sub 4 and so on. It alternates. And that seems really hard to justify. Why would that happen? The endpoints only have 1 each, just like here. Okay, why is that the case? Why does this endpoint only get 1 and that endpoint only get 1? And I guess one way of thinking of it is this endpoint is only half of the base. It's only half the bases of one trapezoid. So you kind of pair this one with that one, right? These kind of pair up, and that gives you that kind of missing trapezoid, right? You have this one paired up with that one. And those are sort of averaged together, which I think is kind of cool. So in Simpson's rule, you have a different situation. Notice that it alternates 4, 2, 4, 2, 4, 2, 4, 2. But what about these ones here? Well, those are on the endpoints, right? And so if you kind of just mush them together, those kind of have a weight of 2. And so it kind of goes 2, 4, 2, 4, 2, 4 all the way across, okay? So anyway, if you're going to memorize Simpson's rule, what you need to understand is that the outermost y values, this is basically the value of the function evaluated at A, and this is the value of the function evaluated at B, okay? Those get a weight of 1, okay? And then the next most ones all get 4s. So you do 1 times these, then you do 4, then you do 2, then you do 4, then you do 2, okay? And so the weightings are always that way, okay? And so that's how you do it, all right? Now, I didn't derive it for you. It's rather complicated to work it out. So let's do this. You'll be asked to do this sort of thing on the homework. The homework's out of the book. It says, use Simpson's rule to approximate the area under this curve using 4 subintervals on the interval from 1 to 9. Okay, and so we need to first calculate what h is. Well, h is the width of each. So it's 9 minus 1. It said 4 subintervals, so that's even, okay, which is good. And so I end up with 8 divided by 4, which is otherwise known as 2, okay? So each width is 2. So the first x coordinate I will use is starting at 1, and then I will add 2 each time. So I add 2, and I get 3, add 2, I get 5, 7, and 9. It ends where it should at 9, just like so. Okay, and now I need the y value, so I'm going to bust out my calculator to do that. Y equals x to the third minus 5x squared plus 20, like so. Okay, and then I'm going to use my table, and I'm going to have it tell me the values at 1, 3, 5, 7, and 9. And those of you who are sophisticated with this know that there's other ways to do this on your calculator. I like the ask feature just as my default, because we do so many things where you do have to put in particular values. So what it's telling us, the y value is 16, and then 2, and then 20, 118, and 344, like so. All right, let me just see that I have the same thing here. Okay, and then the pattern is this. You always put 1s on the outside. So you always do 1 and 1. And then you do 4s next. The next innermost ones, you do 4s. And then all the others alternate between 2 and 4. And you always end up with a 2 in the middle, okay? Because you have to have an even number of subintervals. So you're evaluating the function in 5 places. So there will always be a middle one because you start with an odd number, okay? And then what it says to do is basically just multiply everything by its weight. So 1 times y sub naught would be 16. 4 times y sub 1 would be 8. 2 times 20 is 40. 4 times 118, let's see, that's 472. I'm just copying off my work last year. And 1 times 344 is 344, like so. Okay. So then what I do is I add those all together. 16 plus 8 plus 40 plus 472 plus 344, and that works out to 880. Okay, and remember, the formula says to do h over 3. So the total area, according to Simpson's rule, is h over 3. So that would be 2/3 times 888. All right, and what's really handy about that is, oh, I'm sorry, it's not 888, it's 880. Okay, there we go. All righty, and you guys, unfortunately, 880 is not divisible by 3. If you do 8 plus 8, you get 16, and that's not divisible by 3. And so I'm just going to have to work it out, and let's see what it is. You guys, I don't want you to lose your ability to do fractions. 880 times 2/3, we end up with 586 and 2/3. You should recognize that decimal as 2/3, okay? So it's 586 and 2/3 square units. Okay. All right. And then one really cool fact about Simpson's rule is, you know, for a trapezoid, it uses lines. So you get a perfect approximation of a linear function using the trapezoidal rule. So you would think for Simpson's rule, it would work perfectly for parabolas. But the amazing thing is it works for cubics as well. Simpson's rule will give you the exact area for a cubic function, even though it's using approximations of parabolas, which seems impossible. How does it work that way? And the reason is that basically, because you're having an even number of subintervals, basically what happens to it is, I think this is really cool. See how this one underestimates and that one overestimates it with the trapezoidal rule? What basically happens is when you have an even number of subintervals on a cubic and you use parabolas to approximate, you do the area under a parabola to approximate those areas, what happens is that the overestimation of one will exactly cancel out the underestimate of the other every single time. And so it's really cool when you use Simpson's rule on a cubic, it actually gives you the exact area. And so what I'm telling you is, because this is a cubic, Simpson's rule will give the exact area. And so if I actually do the integral from 1 to 9 of x cubed minus 5x squared plus 20 with respect to x, I multiply everything by dx. If I integrate this, I get x to the 4th over 4 minus, what would this be? 5x cubed over 3 plus 20x plus c, evaluated at 1 and 9, and actually work that thing out. You'll see what ends up happening. So I have 9 to the 4th power. Okay, I have 6561 over 4, and then minus 5 times 9 to the 3rd power is 3645. Let me see about that. Because this is a multiple of 3, when I divide this by 3, I should get a whole number. So I end up with minus 1215. Okay, 20 times 9 is 180, and then plus c, like so, right? And then I'm going to subtract what I get if I put a 1 in here. So minus 1/4, minus, put a 1 in there, minus 5/3, and plus 20 plus c, like so. Okay, and so I end up with, let's see here, 6561 over 4 minus 1/4 would be 6560 over 4, right? And then I'm going to end up with minus 1215 plus 180. The c's are going to go out, plus c. Okay, I've already done the minus 1/4, so I'm going to do plus 5/3 minus 20 minus c. And so this, I'm just going to simplify this. The c's go out like so. And so I'm going to gather my like terms here. 6560 divided by 4, I think that's going to be a whole number, right? 1640 minus 1215 plus 180. Okay, trying to get all this on the same page at the same time. And minus 20. Okay, like so, 585 plus 5/3, like so. There's the same exact answer I had a few moments ago, 586 2/3, and that's exactly what we have here. Okay, so it's pretty cool where your 2 wrongs make a right. You know, Simpson's rule over approximates one section, but then the very next section, it exactly underestimates it. So the 2 areas completely balance out, which I just think is the coolest thing. So Simpson's rule will exactly work for a cubic, even though it's using a parabola to approximate the curve, which I just think it's kind of an added bonus and one of the cool things about math. Okay, you guys, that's our notes. The homework tonight is out of the book. Okay, so there you have it. All right, it's, as always, it's been an absolute pleasure. Okay, so let's take care. All right, I'm gonna stop sharing and I'm gonna say goodbye. Okay, take care. Bye-bye.